Hello, my name is Marie-Agnes Tellier. I am the Senior Environmental Statistician at Trihydro Corporation, a national environmental and engineering consulting firm with nearly 500 employees, 20 offices, and staff resources in 28 states. A few years ago, when I first joined Trihydro from the academic world, I had to get familiar with the federal, state, and local environmental regulations and their statistical requirements and recommendations. To my surprise, most statistical methods published in those official guidelines assume no spatial variation, complete random sampling design, and do not take into account spatial correlation among the sampling locations. Dealing daily with remediation projects, those standard methods do not address site complexities nor sampling limitations. Today, I would like to show you how the standard method put forth in those guidelines to estimate population means and their confidence limit may fail you when their assumptions are not met, and how alternative methods such as the area-weighted bootstraps and spatial Bayesian models could deliver more accurate and precise estimates, thus helping you making sound decisions with potential health, environmental, and economic consequences. The usual workflow in environmental statistics starts with a few samples, anywhere between 8 to a few hundreds, because taking a census is not feasible. From there, one will calculate an estimate of the population mean and often the 95% upper confidence limit around the population mean, often referred as the 95% UCL. In corrective action monitoring for a specific constituent, the 95% UCL would be compared, for instance, to an environmental standard or cleanup goal to determine if remediation has been achieved. Or, in risk assessment, it could be used as an upper estimate of a contaminant concentration in conjunction with contact rate, exposure frequency and duration, average body weight, and average time spent at a site when estimating reasonable maximum exposure. So why use the average? Why use the UCL? The average concentration is generally recognized as the most representative estimate of the concentration that one would get in contact with at a site over time. In addition, carcinogenic and chronic non-carcinogenic toxicity criteria are based on average exposures. But because the estimates for the mean population is derived from samples and not a census encompassing all possible samples, the sample mean is subject to the intrinsic variability and uncertainty associated with the population heterogeneity and errors in the samples. So, for instance, the 95% UCL is used to estimate reasonable maximum exposure rather than the sample mean and hopefully avoid underestimating health risk associated to the presence of a contaminant. The standard method used to estimate the population mean and its 95% UCL assumes temporal and spatial stationarity across the site. That is, no trend or variation in time or space. Here are the formulae presented in the federal guidelines for the mean and the 95% UCL when one can assume the underlying population to follow a normal distribution. If the population is not normal, then identical formulae are available for the gamma and log normal distributions, as well as for non-parametric approaches. However, there are potential issues with those standard estimates. As mentioned before, the standard method assumes no spatial variation in concentration across the site, when most likely there would be not only intrinsic heterogeneity in concentrations of a constituent because of the non-homogeneous nature of everything, let it be soil, air, or water, but also an expected decreasing gradient in concentration of a contaminant from its source. In addition, those standard equations are designed for data coming from random samples, when in reality it is often not the case. The locations are often chosen as a compromise between target sampling and convenience sampling design. Most often, the sampling effort is not balanced. In hope to not underestimate health risk, for instance, it may be decided to target areas around hot spots. Or if one wants to find the boundaries of a plume, then the project team may focus its efforts on area away from the source of contamination. Despite these well-known issues, the spatial distribution and correlation of the samples are almost never taken into account when estimating the population parameters. The first spatial method we are proposing relies on an area-weighted bootstrap of the standard method. As shown on this figure, for a sample of size n, here 50, a Voronoi tessellation is defined such that all the points within a polygon are closer to the reference point, that is, the sample location, than any other reference point at the site. Consequently, each sample location is associated with a polygon and an area that sums to 1 with all other areas. These areas are used as weight or selection probability when performing the bootstrap sampling. For each bootstrap sample of size n, we would apply the standard method to estimate the mean at a 95% UCL. So, if we want to perform 1,000 bootstraps, the estimates for overall area-weighted bootstrap mean and 95% UCLs would be the mean of the 1,000 area-weighted means and 1,000 area-weighted UCLs. One could, of course, consider the median rather than the mean of the bootstraps estimates if outliers are of concern. The second method we considered shifts our statistical evaluations from frequentist to Bayesian inference. Here, rather than determine a Voronoi tessellation, a 2D mesh based on Delaunay triangulation is defined. Great care should be taken when defining the mesh. Its triangles should be as close in size as possible, and the mesh should extend beyond the domain by at least 1 time the range. Assuming an underlying normal population distribution of the response, a hierarchical model can be set up where, for instance, aside from the sampling error sigma e, the mean concentration at a location I is only the result of a mean intercept B0 and some random spatial noise of mean 0 and a Matern spatial covariance. Using stochastic partial differential equations or an integrated nested Laplace approximations, one can quickly and reliably estimate the posteriors of the model's parameters and hyperparameters. From those posteriors, 1,000 draws can be performed, and for each draw, a site-wide linear predictor, here mu hat d, can be estimated, taking into account the size and location of each triangle inside the domain. As for the area-weighted bootstrap method, the overall Bayesian spatial estimates will be the mean or median of the draw estimates. However, because we have stepped into the Bayesian realm, this method will provide a 95% credible interval rather than confidence interval around the population mean. To assess the performance of those two proposed methods in comparison to the standard method, we perform 500 random simulations of size n equal 50 in a 1x1 square, similarly to the SPD toy example from the R inlet package, but under 5 different scenarios. Scenario 1 followed the model previously described. It assumed no spatial gradient, a small spatial variance, and random samples across the domain. In comparison, Scenario 2 assumed a large variance. Scenarios 3, 4, and 5 assumed a small spatial variance like Scenario 1, but also a spatial gradient from the origin 0, 0, with concentration decreasing twice as fast along the y-axis as along the x-axis. While the sample locations for Scenario 3 were randomly selected, scenario 4 favored the bottom half of the domain close to the source, and scenario 5 favored the top half. Values for the parameters were chosen so that, regardless of the scenario, the overall mean concentration of the entire domain was 10.25. Here are some of the results of the simulations. For all scenarios, the spatial Bayesian method performed the best. The mean absolute error, root mean square error, mean absolute percentage error, and the relative standard deviation are all the smallest for the Bayesian approach, followed closely by the area-weighted bootstrap method. As you may have noticed, the percent cover for the Bayes method was always between 65 to 70% across all scenarios. This was probably due to the fact that one mesh and identical priors for the Mattern covariance were provided for all 500 simulations rather than tailored to each dataset. One would expect in real settings to obtain coverage estimates close to the ones obtained with the area-weighted bootstrap method. As expected, when assumptions of no spatial gradient and random samples are met, all three methods perform similarly, regardless of spatial noise. However, when a spatial gradient and concentration is present, the standard method starts showing trouble with a larger variance among its estimates compared to the two other methods. Where the two spatial methods shine is when the sampling effort steps away from the random sampling. While the standard method will follow the effort, that is, overestimate the parameter if areas close to the hot spots were targeted, or underestimate the parameter if the locations with low concentration were mostly sampled. The area-weighted bootstraps and the Bayes methods take into account the spatial information associated with each sample to report an unbiased estimate of the mean and therefore 95% UCL. Here is an example based on particular matter 10 at 24 location on November 16, 2005 in Piemonte, Italy. The area-weighted bootstrap method used 24 Voronoi polygons, while the Bayes method used 298 vertices. For the Bayes approach, the latitude and longitude were first considered as covariates in the linear predictor in addition of the mean intercept. However, the credible intervals associated with both slopes parameter included 0. Therefore, the results presented in this table are for the Bayes model, including only the mean intercept in the linear predictor. Even though the Bayes model showed no evidence of a spatial gradient, the standard method seems to have overestimated both the mean parameter and the 95% UCL. In summary, while the standard method performs adequately when the assumptions are met, even in the presence of large variance, in the presence of spatial trends, it shows a decrease in precision if the samples are randomly collected and can fail to provide an accurate estimate of the population mean and UCL outside random sampling design. In our simulations, area-weighted bootstraps and spatial Bayesian methods perform adequately in the presence of spatial gradients and non-random samples. While area-weighted bootstrap method may be simpler and more user-friendly, the Bayesian approach can be extended to test and include the effect of additional covariates, like we did with the lat long in Piemonte. One could test the effect of precipitation, elevation, geological ground type, or season on the mean concentration estimates and potentially get a refined estimate for each relevant condition. The Bayes approach can be used to predict the average concentration on a grid or location of interest where no information was collected and potentially identified hotspots. While we use continuous mesh here in this presentation, barriers and no access inclusion can also be considered. If you have any questions, please feel free to contact me. My email was on the second slide of this presentation. Thank you. Goodbye.